Okay, y'all, let's get started. Good of you to come on a rainy day. As I came past the parking lot that I use, or used to use, but it's now a commuter lot, there were all these open spaces, and I was thinking, wow, rainy, dark days like today really do keep attendance down, but it seems like we have a pretty good turnout here, so that's great. We are finishing up our introduction to pointers today, and then we're going to move into lists and stacks and DQs. So that will be our second big data structure that we're going to be talking about this semester. So before we get to them, I just wanted to do a few more things with pointers today. I wanted to, again, quickly go over the two big problems you'll get with pointers. Then I wanted to go through and have you draw out a diagram for the Facebook server that Dr. Plank has in his notes. Yesterday in lab, you kind of worked a exercise with GDB with it. Today, what I want to have you do is draw pictures with it, and that's what the worksheet coming around is for. So when we get to that, I'll talk about it, but first, a couple of things about problems with pointers, which we talked about at the end of last lecture, but it was a little rushed. Not so much the memory leak, that wasn't rushed, but just a reminder that if you forget to return memory to the memory allocator or to the heap via the delete operation, then it will never be reclaimed. So when you lose a pointer to a heap object, like what is done in this little example where we create a new integer that IP1 points to, and then immediately create another new integer that IP1 points to. We lose the integer or the pointer to the first integer, 10, it becomes a memory leak. And as I've said a couple other times, you have enough of these memory leaks in your program and it eventually crashes because when if new is unable to allocate memory from the heap, it throws an exception and your program terminates. So that's why you don't have to check to see whether your program gets memory when you call new. If new is unable to get enough memory to hold a value of the specific type because the heap is essentially depleted, then it throws what's called an exception, which we won't talk about in this course, but your program terminates. Much like when you use the at method with a vector and you try to access an invalid entry in a vector, it also throws an exception and your program terminates. Okay, the good news about memory leaks is they actually, I'll get to you 1 second. The good news about memory leaks, they don't affect the correctness of your program in the sense that if your logic is correct, your program will run to completion. It will produce the correct result. So it's kind of an invisible error, only evident if your program runs for a really long time and eventually terminates because it runs out of memory. Yes? I don't care which you use. If you were going into production, then I would care. Then I would tell you needed to use these square brackets because they're faster, because they don't do any checking, okay? But if I was in the real world and I was your manager, I'd say during testing and debugging use .at, and then when you were ready to go to production, change them all to square brackets because they're faster. But I hate to say, I don't want to say, but .at's a little like training wheels because they make sure that if you make a mistake that you'll immediately catch it. But I still don't care which one you use because it's not that big of an issue, okay? Okay, so the second problem that we talked about last time is the dangling pointer problem, and that's a more serious issue. So a dangling pointer occurs when you delete a piece of memory prematurely, and you have some other pointer that points to that memory, and you subsequently use that pointer. We call it a dangling pointer because essentially, like dangling off a cliff, the piece of memory it points to is gone, okay? But it can cause a lot of damage, as I showed you with that program at the end of the period last time, and it was a little rushed. So again, I'm going to show you that program. So what I was trying to do is create a situation where, actually it's easier to draw it. So let me also put up this thing next to it. So, and try to, because it often helps when you have a picture of what's going on. So what I have on the left, I have created some pointers to strings, name and name one. I've also created a pointer to a picture. Up here's my picture. It just has rows, columns, and a name. Very simple object. So initially, I create a new object off the heap, and I make name point to it. So initially, name points to this object on the heap, and it has the string Brad Vanderzanden in it. Okay, and I'll say that it is at memory address 0xa000. Okay? So my next statement, I make C1, or I'm sorry, I make name one also point to name. So at that point, I also have name one. So they both have the memory address 0xa000 that they store. Okay, and I print it, whoops, that's no good. Okay, so next I print them out, and basically I print out the address of name, and given what I just told you here, the address would be 0xa000 that it was storing. And then star name would be Brad Vanderzanden because that's the content of the memory to which name points. Now I come down here and I delete name, which means I return it to the heap. And right after I delete name, I allocate a picture object, and I assign it to picture pointer. And this is what happens. So first of all, I gave back this piece of memory, but the memory allocator doesn't zero it out or anything. It still has Brad Vanderzanden in it. And then I replace it with a picture object. So now the picture object is being stored at 0xa00 because that's the first piece of memory available. I gave it back. So now picture pointer also points here. Whoops, didn't want to move it. So we also have picture pointer. So they all point to this piece of memory. Okay, so except that conceptually you should now think of this memory as being organized by rows and columns and a name. So it now has rows, columns, and a name. Okay, uninitialized because I don't have a constructor, so these fields all have question marks. Okay, now I set them to something, 10, 20, and smiley. So I set rows to be 10, columns to be 20, and I'll just put an S here for smiley. Okay, so I've set the values, and next I go ahead and I print out the contents of picture before being overwritten. So I print out the memory address stored by picture pointer, which is, if I print out picture pointer, what is going to be printed out? I see we're listening carefully. Okay, So picture pointer points to this piece of memory. So what's going to point out? Print the address, which is 0xA00. So the address for picture pointer will be 0xA00. And when I print out rows and columns, it prints out 1020 and the name is Smiley. Now, name1 is a dangling pointer. So I deleted name, but name1 still points to this piece of memory. It still has the memory address 0xA000. And I go and I change it. I set name1 to be equal to data structures and algorithms. And C++ is very obliging. It changes it to data structures and algorithms. Okay, so this thing gets all messed up. It now gets changed to be data structures and algorithms. Okay, that's not too good because name1 doesn't really own that space anymore. It belongs to picture pointer. So now I go and again, I naively, well not so naively because I want to show you what happens, I try to print out the memory object for picture pointer. And now I get garbage. It really is indeterminate what's going to print out. And the reason is that what occupies rows might be, for example, the 4 characters DATA. Remember, 1 character per byte. An integer has 4 bytes, so it may well be that the ASCII codes for DATA is there for row. Well, row is interpreted as a 32-byte integer, not as 4 ASCII character codes. So whatever prints out is going to be whatever is the 32-bit representation of DATA, which is a complete bunch of garbage. Same thing for columns. It might have, say, blank. So for columns, what might be currently stored there is an underscore STRU. I'm sorry, STR. Again, absolute garbage in the columns thing. And finally, for name, it's really garbage. Its name may start at U at the ushers, and it's really not at all clear because if the size is the first variable in the string, then there's really nothing. Again, the size variable might be UCTU. It's just garbage. Okay? So what I'm trying to do is give a picture to what happens when you have a dangling pointer. And that picture is that a dangling pointer can overwrite a piece of memory with garbage. And that, in effect, corrupts whatever is the legitimate pointer to that object. Okay, and now when you try to access that memory object through picture pointer, what you get is corrupted memory. In one case, you just may get bad data, like a really weird number for rows and columns. But if I had a pointer in picture pointer, then I would end up probably with a seg fault because that pointer would have been overwritten with a bad address. Okay, and so your code would seg fault and you'd be really puzzled as to why, because you never changed the pointer in picture pointer. Okay, so just to show you, let's run this program. So it's pointer dangling. And you can kind of see what happens. Name gets this memory address, 0x7FC65. And you can see that picture gets exactly the same memory address. If you look at the 2 memory addresses, this address is exactly the same as that one. So what I told you is true. Picture pointer got the same memory. So initially, when I assigned it values, it has the values I expect, 10, 20, and Smiley. But after I assigned data structures and algorithms to name1, you can see that picture pointer is just garbage. Rows is 49, columns is 0, name is just some real garbage. Okay? So this can easily happen to you with dangling pointers. And it manifests itself by a piece of memory mysteriously changing without your ever touching it, seemingly. In this case, it's like a magic, like I'm a magician. It's like I was able to change the memory object associated with picture pointer without ever touching it, except in a bad way because your memory changes unexpectedly. And you're like, this is the worst kind of bug to have to find. Okay, first of all, it doesn't usually manifest itself as soon as you make the error. Okay, so when I assigned data structures and algorithms to name 1, I might do a whole bunch of other operations before I ever try to access picture pointer. And then I access picture pointer and its contents are corrupted, and it really could be any place in the program that I had my dangling pointer. Basically, you're now having to try to search for your dangling pointer. GDB will do you almost no good in this situation, okay? Other than to tell you, hey, if there's a seg fault, it occurred when I tried to go through a pointer in picture pointer. You probably have to use printf statements or cout statements, print statements to find your error, because what you have to do is keep printing out the value of picture pointer until you find a place where it's still good. So what you have to keep doing is printing out where it's good and where it's bad, and you kind of are moving the window smaller and smaller. It's like you have a window of code where the bug could be. Above the window, picture pointer is perfect. Below it, picture pointer has been corrupted. And so you keep moving the window closer and closer until you catch the bug. And that's pretty much the only way you can catch a dangling pointer. They are nasty. They can easily take you a couple hours to figure them out. Okay, and I have spent easily that much time on them. The more complicated the program, the longer the time you'll have to spend on them. Yes?
Aren't things even more complicated as you're trying to narrow the window down? Some of your runs might not produce the bug.
Yes, so John's right. The problem is that another issue is the results can vary from run to run because sometimes your memory allocator will generally give you the same chunk of memory as name, but on a bad day something happens and it doesn't give you the same chunk of memory, and mysteriously it does work that time because it gave you a different chunk of memory, and now when you overwrite this memory object with name 1, you're no longer overwriting picture pointer. So it can be even more pernicious especially if you come back several days later or you try to debug it on a different machine with a different compiler. So normally you got to make sure it's on the same machine, same compiler. Try to debug it right away, okay? Or else even closing up that gap may be hard. Okay, so these are really pernicious. Other issues. Okay. So, moving on, like I said, with pointers, it's really helpful if you draw pictures, okay? And on the exam, midterm 2, one of the things you'll have to do is draw pictures. So yesterday, you were dealing in lab with Dr. Planck's Facebook server. Dr. Planck likes to always play with words, so I'm sure that you saw the correspondence with Facebook. And you were writing a little server program that was essentially accepting commands from users, and it was a small social media program. And the commands you were allowed to give it was a new person, to add a new person to your social media. You could change their mood. You could put them in a relationship with someone else, although it didn't have to be bidirectional. The in relationship simply was your assertion that you were in a relationship with another person on Facebook. And you could add a friend, and again, it's one directional. You're just saying this person is a friend of yours. And then you could do a query, which would print out the information about a person. Okay? And there is some code that, well, first of all, there was the data structure. So each person had some information associated with them, a name and a mood. If they were in a relationship, then there was a pointer to the person to whom they had a relationship with. And they have a vector of friends, and that vector is a vector of pointers to persons. Okay? So what he then does is goes through and shows you some of the code for doing it. So first of all, he was using a hash table to assign or to store people, and he was using the DJB hash function to compute the hash index, and then he was hashing it into a table and storing the person's name. And you can see initially we have this null constant, so remember null means that we don't point to anything, and he pushes the person onto the appropriate bucket in the hash table. And then he has some basic things. So here's his code for creating a new person. He first checks to make sure the person isn't in Facebook already. Just like when you try to add yourself to Facebook, you have to give it a username, and if that username is taken, you're not granted it. So we always want to make sure that you're not trying to add yourself when someone else already has the same name. So if that person already exists, we just print unsuccessful. Otherwise, we print that we are successful. Okay, and find person. Let's see. So with his find person, he is also able to control whether it just returns. So with this flag here, false and true, he's able to control whether the find is simply returning a pointer to the person, or if true, if it doesn't find the person, then it actually tries to insert a person. Okay, so he's having his find person do double duty depending on whether the flag is true or false. False, it's simply returning the person, or null if it doesn't find it. True, if it doesn't find the person, then it creates an entry for that person and returns it. Okay? And you'll see he's passing in N1, which is the line that he read, so that he can break up that line into some information and create the person. I know I'm going through this quickly. To really understand it, you have to look at the code afterwards, which is pretty much always the case. Okay, if it's the mood, then what he does is he finds, again, he tries to find both the, he tries to find the person, and if he finds the person, he sets their mood to whatever mood is. Okay, so mood is a string, it's coming in from CN. So that's pretty simple. And with his query, he simply prints, he again finds the person, he prints out all the information he has with the person, the name and the string. Thus far, he doesn't have friends or in relationship yet. And he likes to use printf. It's fine if you use cout, but if you use printf, you have to remember to use the .c_string. Okay, then he gets to doing in relationship. And for a relationship, it's between two people. So he has to get two names, name 1 and name 2. And he has to find both of those people in the hash table before he can do anything. So if he succeeds, then he sets the in relationship pointer for person P to point to the P2 object. Okay, so this shows you the value now of pointers because we are able to point to the person we're in a relationship with. Okay? And then finally, with add a friend, it's roughly the same thing. We get the two names, we find the two people. The only difference is that instead of changing the in relationship variable, we now push back person 2 onto the friends. Okay? And does anyone see a slight bug, a subtle bug in this code? It won't segfault, okay? That's not the issue. Okay, it's hard to spot, and the reason it's hard to spot, I'll give, yes?
Is it because if you exit right away, you won't be allocating memory?
Nope. If you exit it right away, you don't have to deallocate memory because it gets reclaimed. That, remember I said at the end of a program, you don't have to delete. Okay? Yes? Pardon? No, it is one directional. So it's not, if I say you're my friend, you could say, oh my God, I hate Brad. He's not my friend. Okay, so it's, so this is an example of what is not there. Okay, so like when the Sherlock Holmes story where the detective said, is there anything else? And Sherlock Holmes says, yes, the curious incident of the dog. And the sheriff is puzzled and says, what about the dog? Nothing happened with the dog. And Sherlock Holmes says, exactly. The fact that the dog didn't bark indicated that the dog was familiar with the intruder. In this case, it is the fact that he didn't check to see whether P was already friends with P2. So you could end up with multiple instances of P2 being a friend of P. Okay, he never checked that. In your hash tables, you always check that. Before you insert a key, you make sure that the key isn't already in the table. He did not do that here. So he could end up adding me as a friend multiple times to the same person. Okay, a subtle thing. But that's another check that really should have been in the program. So that's an example of something subtle that's not there. Okay, and then to print out the friends in query, he simply iterates through the friends array. He uses this arrow. Remember, we often use arrows to get to the fields of objects. So if a pointer is pointing to a primitive type like an integer or a char or a bool, we use a star. But if it's pointing to a object, we use a arrow to get to the fields of or methods of that object. So we go to friends I, that returns a object, a pointer to a friend, and then we go through that friends object to get their mood. Okay, so we're always printing out the mood of the friends. Now, none of you have asked this question, but it would be reasonable to say, hey, Brad, with strings, which are objects, you use star rather than the arrow. And that is true. So strings are not a primitive object. They are a class, and yet we use the star with strings. And the reason has to do with something called operator overloading. It is possible to overload operators like stars so that they do different things like print out a nice value. And that's what they did with the string class. So they made star work properly with the string class so that it would print out the name of the string. But in general, you don't know how to do that. So to access the member functions or member variables in a object, you're going to have to use the arrow. Okay? So we come to your worksheet that you have in front of you. And you can see here that Dr. Plank is doing a bunch of things, and I want you to take about 10 minutes to do this yourself. Now, I've created already the 4 persons for you: Scarlett O'Hara, Rhett, Ashley, and Melanie. What I want you to do is do the remaining commands that you see in this table: add friend, in relationship, and mood, which means you're going to have to start drawing arrows between the different people. Not only that, but I want you to add them to the hash table. So he has given you the hash keys. Here are the hash keys for Scarlett, Ashley, Melanie. So write them down if you don't have a computer, because you will need these, because I'm going to go back. All you need is the last 2 digits. Don't worry about anything else. So Scarlett is 37, Rhett is 22, Ashley is 18, Melanie is 08. Actually, you really only need the last digit if I want to make it somewhat interesting. Okay, so go ahead, take about 10 minutes and execute the add friend, in relationship, and mood, as well as making the hash tables. The hash table itself, you have to make the hash table point to the appropriate people. You are using separate chaining. So if 2 people hash to the same bucket, you will have multiple entries in that bucket. Feel free to work with a neighbor. Pretend this is a test question.
Melanie's feeling pious.
Oh, hash table size is 10. Sorry.
You got like a whole backstory. Ashley doesn't know about it. Wait, neither was Red. Ashley or Red. It's a terribly awful situation.
Yes, it is. You've never seen Gone with John, have you?
No. Friends with one, but not friends with the other.
Remember, this is also Dr. Plank's analysis of the script.
No confidence. I like the pious. That's really
Well, that is true.
Yeah.
In the movie.
Really? It matters is if you have values. Wow. So you could say in relationship or you got that. Other than just saying like, I'm in a relationship.
Scarlett's like, oh yeah, I'm with him.
And none of them have one.
That's kind of like the dramatic thing on Facebook. Like 10 years old. There's like one class that is like because you know they don't have to wear.
Yeah.
So then what the hell?
Yeah.
Oh.
I think it's like, there's like gonna be a hard suit, and it's gonna be the same.
Oh yeah, that has to.
It's like,
So red.
no, like, I think it's like into, not like ambiguous.
Melanie.
They're just like a place.
Actually, they're in the same book.
I like it. I mean, anything that Jordan is. That's not really.
Yeah, I mean, it's point of the same.
How did the French work? Are they supposed to be Arabs too?
Melanie.
So that one was, yeah, I thought so. That one. I knew that one.
That's a lot of arrows. It's a complicated business.
Pardon? It is kind of, if I remember the movie, kind of slouched in like limp. It spineless.
Oh, that's a good.
That is what he was going for. Let's just say of the characters in Gone with the Wind, Ashley is perhaps the most annoying. Pardon? Yeah, I agree. The whole movie was kind of annoying. My dad loved it, so I had to watch it a fair number of times when I was a kid, and it is a long movie. When it was shown originally in the movie theaters, I'm told there was an intermission. It was so long. Yep.
I think the Friends eras. I don't know.
That was like elementary. Then it was it's in a relationship.
So it's probably one of those things.
I wanted to see like physically what's going on.
Okay, I'm going to give you about another minute, and then I'm going to go over the answers. Okay, so going to go over the answers. Just a quick question. How many have actually seen Gone with the Wind? Okay, a fair number of you. It is a long movie. So, and a fun fact, it came out the same year as Wizard of Oz. And Wizard of Oz was a big bust because Gone with the Wind was so popular that Gone with the Wind was the blockbuster. And Wizard of Oz basically made it on TV many years later. So they both came out at the same time. Both well known because Wizard of Oz and Gone with the Wind are both two of the first movies made in color. Okay, so as opposed to being dubbed back into color like Casablanca. Okay, so here's the answer. I know it is in the notes all the time, but I want you to do it because if I go over it, you'll just listen to me. Active practice is always better for learning things. So on an exam, try to do kind of what Dr. Planck did. Draw little boxes if you have a vector. So we had that, I know this is, I have to make it still a little bit smaller. So the hash values, the hash table was 10 entries, so the hash table size was 10. So you're modding everything with 10. And given the hash values that I showed you earlier, Rhett is the one person that hashes to entry 2. So the second, or the bucket with index 2 is going to point to Rhett. And Scarlett had a 37 ending, so 37 mod 10 is 7. So bucket 7 points to Scarlett. And then Ashley and Melanie, how sweet, because they were in a relationship, both had last digits of 8. Melanie was 08. I forget what Ashley's was, but they, pardon? 1-8, thank you. So modding by 10 gives 8 for both of them. So you see there's 2 entries in the vector for this bucket. So 1 points to Ashley, 1 points to Melanie. Then Scarlett had 2 friends. So you can see that her friends, one of them points to Ashley, one of them points to Melanie. And she is in a relationship with Rhett. So, or should be in a relationship. Did she not? Ah, there we go. Sorry. So, there we go. Snaking out of in relationship is the red arrow down to Rhett. So she's in a relationship with Rhett. Rhett said that he was in a relationship with Ashley. So you see this red arrow coming out of in relationship and going up to point to Scarlett. Sorry, did I say Rhett said he was in a relationship with Ashley? I meant Rhett was in a relationship with Scarlett. Then Ashley indicated he is in a relationship with Melanie. And likewise, Melanie said she was in a relationship with Ashley. Now, this red arrow really should be coming out of in relationship because that is the actual pointer. But in drawing, sometimes you get these artifacts. Melanie made the huge mistake of saying that she was friends with Scarlett because if you know anything about the movie Gone with the Wind, Scarlett is always angling to get at Ashley's love, or Melanie's love, Ashley. So Melanie may not have wanted to actually friend Scarlett, although keep your enemies close. So at any rate, she has one entry in her vector pointing to Scarlett, and those were the only friend relationships that were established. So if I had this on a test, I would expect you to draw a diagram that looks something like this. And like I said, please, if you have multiple entries in a vector, just draw a little rectangle with some squares, and out of each square have a pointer to whatever it's pointing to. So any questions about that? Okay, yesterday in lab, you actually saw with GDB, you actually saw the hexadecimal addresses that were associated with this. And if you're debugging, it helps to both draw pictures and print out pointer values or use GDB to look at pointer values. So that's our introductory look at pointers. We're going to put them aside for about a week before we come back, actually for a couple weeks before we come back to them. But you are using them in Lab 5, so in your labs you will be using them constantly. So questions thus far about pointers? Okay. So they will be used to implement the second type of data structure that we're going to be talking about this semester, which are lists. And the other things like stacks and dequeues we are going to be talking about can all be implemented using lists. So lists are a very fundamental data structure in computers, just as they are in real life, because we're always keeping lists. Grocery lists, to-do lists, those are the big two, but lists of tasks. So we constantly are keeping track of things via lists. And they are just as ubiquitous with programs as they are in our everyday life. So in addition to lists, we're learning about iterators and bad vector usage, doubly ended queues, and stacks over the rest of today and on Tuesday. So to give you an idea of how they are stored in a computer, so a list is exactly what you think it is. It's just a list of items like a grocery list. And in a computer, we implement them with pointers. So typically, a list is going to look like a list of pointers. So let's say this was a grocery list, and I wanted milk because I'm a big milk drinker, Coke because sometimes we do have to ruin our teeth, and ice cream because, oh my gosh, I try to support the dairy industry in every way that I can. And I have a milkshake every day, which means I also work out every day because something has to give and it's not my waistline. Okay. So we have milk points to Coke, points to ice cream. And that is why we have introduced you to pointers and why we call them linked data structures, because we use pointers to connect the elements of a list. Now, we will get to that in a couple weeks, but I figured it was helpful for you to see what they look like. And we call this a singly linked list. because the list is one directional, okay, or we say unidirectional. Okay, more often what we have are doubly linked lists, where not only do we point to our successor, but we also point back to our predecessor. What I've just drawn is called a doubly linked list. It is bidirectional, and you can traverse it in either direction. So you can either go front to back or back to front, which is very helpful, which is why typically lists are implemented as doubly linked lists. So they have both a pointer to the next item on the list and a pointer to the previous item on the list. Okay? So that is how they are implemented. You're not going to have to worry about that just yet, because we first want to get you into the habit of using lists, and then we'll talk about how they're actually implemented. So lists are implemented in the STL, or Standard Template Library, just like strings are, just like vectors are. And if you want to use them in a program, you say include list. That will bring the list in from the Standard Template Library. To declare a list, you have to say what type of value it is storing. In this case, we are storing strings on our list, so we say list arrow string. So this looks just like a vector, because when we have a vector, we also have to specify the type of value it stores. Now, when we traverse a vector, we've been doing it using indices, 0, 1, 2, 3, 4. That is not how we traverse a list. So a vector, you can in effect hop right into the middle of a vector. Anywhere you want, you hop right in with the index. But you can't do that with a list. To traverse, get to an element of a list, you typically either have to start at the beginning of the list or the end of the list, and then you have to move through the list element by element. And we do that using something called an iterator. An iterator is something that keeps track of where you are in the list. So an iterator is effectively a pointer to the item that you are currently at in the list. Okay? It's a little bit like a cursor on your screen, except the cursor is always between letters. An iterator is always pointing directly to the item that you are currently at. And you can have more than one iterator at a time going through a list, as we will see in an example on Tuesday. So to declare an iterator, it is you give it again the type of list it will be iterating over. In this case, it is iterating over a list of strings. You see the double colon and then the word iterator. And LIT does not stand for literature. And the reason I say that is because every time I look at it, I think of literature, but it actually stands for list iterator. And in this first very simple program, all Dr. Planck is trying to do is reverse a list. So if he has the elements milk, Coke, and ice cream, he wants to print them out actually in the order ice cream, Coke, milk. That is, if his input is in the order milk, Coke, ice cream, then he wants his output to be reversed, meaning he will first print ice cream, then he will print Coke, then he will print milk. So he's simply reversing the order of the input. And to do that, what he is doing is pushing items onto the front of a list. So what he is doing is, if he first reads milk, milk gets put onto the list. Here's milk. Then he gets another line. He sees push front. So push front is adding something to the front of the list. Remember, push back put something onto the back of a vector. And in fact, push back also puts something to the back of a list. But right now, he is adding things to the front of his list. And Coke is the second thing he reads. And ice cream is the final thing he reads. I'll just put ice in a C. So when he's done, he has a list that looks like this. Ice cream is the first element. Coke is the second element. Milk is the third element. Now he has to traverse that list and print out the contents. We do that with a iterator. So we set the iterator, LIT, to be lines.begin. And that makes the iterator point to ice cream. So right now, lit points to ice cream. And it says while lit not equal lines.end. And you might think, oh, since lit.begin returns a pointer to the first item of the list, lines.end must return the last item of the list. And you would be wrong. Okay, so it turns out that there is something at the end of lists called a sentinel node, which we'll denote with a big X. There's also one at the front of that list, but I don't have room to put it there. So at the end of the list, just a second, Nick, there is something called a sentinel node. And the iterator is actually returning a pointer to that sentinel node. Okay? So what we are doing is actually iterating until we have exhausted all the elements of the list. So we start with lit equals lines.begin. It returns a pointer to the first element. You'll see that the way we print or get at the value of the element is just like we would with a pointer. If we want the contents of that list element, we dereference it with the asterisk. Thus, starlit gives us the string ice cream. So it's very similar in concept to a pointer. The iterator itself points to an object. If we want the memory contents or the value of the item to which it points, we use the asterisk to dereference it. Okay, so then to get to the next element, we say lit plus plus. And the idea is just like adding 1 to an integer variable, but in this case, we're not adding 1 to an integer variable, but instead, we are advancing lit so that it points to Coke. And we again print out the contents of that list element, which is Coke. And we again advance the iterator using lit plus plus. So it's now at milk. And we print out milk. And we advance the iterator. And now the iterator points to the sentinel node. So when we ask whether the lit is not equal to lines.end, that condition is now false because it is equal to lines.end. So we drop out of the loop. We are done with our program. Nick?
What did you say that end node was called?
A sentinel node. That's a good question. So sentinel node. So think of a sentinel in a camp, a guard. It's like a guard on the list. Okay, so that's why they called it a sentinel node. Yes, John?
Did you say that there's also one in the beginning?
Yes, and I'm lying a little bit because it's the same one. But I don't really want right now to go into why it is the same one.
So when you start at the beginning, are you starting at the first node or are you starting at the second?
Lines.begin returns the first element of the list. It does not return the sentinel node. That's why there's a little bit of an inconsistency here. Begin, so L.begin, okay, returns an iterator, or returns returns a iterator, an iterator. to the first item or first element of the list. Okay? Whereas end returns an iterator to the sentinel node. And you'll hear us, we often talk about the elements of the list as nodes. So get used to me using the word node to refer to an element of a list.
But technically, they're both referencing the single node.
No, they're not technically. Begin is referencing the first item in the list. End is referencing the sentinel node. They are not technically referencing this, both technically referencing the sentinel node. Begin is the first element of the list. Okay? Questions about that? Yes.
So when would a list be more ideal than say
Okay, good question. So the question is, when would a list be more ideal than a vector? And I'm actually going to put you off. Okay. Okay, I'll give you a quick answer. When I need to insert or delete in the middle of it, or so vectors are best when we insert at the end. Lists are best when we insert any other place or delete any other place. And we'll see that when we get to bad vector usage. Okay, so there's an example of why it's really bad to insert or delete in the middle of a vector. Okay. Other questions? Okay. So remember I said that it is helpful to have doubly linked lists so that we can also go in the reverse direction. And C++ actually gives us reverse iterators. So if you want to reverse traverse a list, you ask for a reverse iterator rather than a forward iterator. So if you just ask for an iterator, you get an iterator that goes from the front to the back of the list. If you ask for a reverse iterator, then you get something that is expected to go from the back of the list to the front of the list. So now, what do you think? So this is going to be confusing. That's why I just went, okay. So now Dr. Planck is going to traverse this list. He's going to again reverse it, but now he's going to read in the elements in their natural order and push back. Notice he's using push back now. So we read milk, and it's first. Then we read Coke, and it's second. And then we read ice cream, and it is third. But there's back pointers as well. So we can go in reverse. So now to print it out in reverse, he has to start from the back. He has to print ice cream, then Coke, then milk. So he's going to start at the back and move toward the front. So he needs a reverse one, and this is why I laughed, because it says lines.r begin. And you probably think, oh, beginning of the list. You would be wrong. R begin stands for reverse begin. So R begin stands for reverse begin. That's really reverse begin. And it returns an iterator to the last element, to the last element of the list, which in this case is ice cream. So what do we think lines.r end returns? The sentinel node at the beginning of the list. So out here, at the very beginning, that awful thing right here is meant to be an X. So the sentinel node at the beginning of the list. in iterator to the sentinel node. And to go backwards in the list, we use lit minus minus. No, we don't. We use lit plus plus. Very confusing. So I think the C++ developers just decided they would be consistent and that lit plus plus always means we advance that iterator one element in the direction we are traversing. So lit plus plus means we actually move to Coke. So we started at ice cream. When we say lit plus plus and it is a reverse iterator, it advances to Coke. So the fact that it was declared as a reverse iterator is what allows C++ to know that when we say plus plus, you're going in the reverse direction. Okay. And just so you know, you can say minus minus. And if you say minus minus, it moves the iterator back one. Okay, so it is okay to say minus minus. It will move it back one. Reverse.
Is the arc again different than if you started at the end and incremented one? Like if you primed it with backing up one or going forward one, if it was a reverse iterator. If you started the sentinel node and just back up one, is the arc again different?
Actually, I've never tried that. So it would be interesting to actually start. It should actually be that if you said lit equals lines dot, no, you can't get to it. You can't get to that sentinel node. So actually, that's, yeah, you can't exactly get to it. You can get to it with the forward iterator, but you can't get to it. I'm pretty sure that the C++ compiler will bark at you if you tried to say lit equal lines dot end. It will tell you it's some kind of type mismatch. Yes. John.
Just to be 100%, is it one sentinel node or two sentinel nodes?
There's only one,
But we're moving.
but for our purposes, just like a map, when you flatten it, so I'm flattening it. So for the time being, think of there conceptually as being one sentinel node at the beginning and one sentinel node at the end. Eventually, it's really a circular list. So that is why it comes back. Okay. Other questions about reverse iterators? Okay. Now, that is not where you get the beauty of lists. The beauty of lists is the ability to insert into the middle of a list or delete from the middle of a list. So let's say we have a grocery list, and now the items in my list are oranges, bananas, milk, and orange juice. Okay? So I have that list, and I want to insert yogurt into the list so I have a list. So my list right now is oranges, bananas, and right now I know I'm drawing it as a singly linked list, but they're generally, that you should think of them as doubly linked. So milk, the last one is orange juice. And what I want to do is I want to insert yogurt into this list. And I want to insert it before milk. So what I want to do is right before milk, I want to change that so that bananas is going to point to not that. So we want bananas to now point to yogurt. And yogurt will point up to milk. So we're inserting into the middle of the list. So the way we're going to do that is again with an iterator. So the first thing we're going to do is we're going to find where milk is in the list. So we want to point to milk. We want our iterator to point to milk. So lit should point to milk, and then we're going to insert before it. So we first iterate through the list. This is this code right here. I know, it keeps doing that. How nice. And we are iterating until we discover that we have found our target. So if asterisk lit is equal to our target, we call the insert method for a list. And the list insert method takes two arguments. It takes a pointer to the object that we are inserting before. So insert inserts before. Inserts new item before the node pointed to by lit. And I break to get out of my loop. Okay, once I'm out of my loop, I need to check one thing. Maybe the item wasn't in the list. If it's not in the list, I want to add it to the end of the list. So I check to see whether my lit is equal to grocerylist.end. If it's equal to grocerylist.end, it means that I dropped out of the loop without ever finding the target item. Because if I found the target item, I broke. And in breaking, lit would still point to that target item. So if I get out of that loop and lit is pointing to the sentinel node, it means I did not find the target. In that case, I simply call pushback because pushback will insert at the end of the list. Okay? So if I want to insert at the end of the list, I use pushback. If I want to insert at the beginning of the list, I use push front. If I want to insert in the middle of the list, I use the insert function. What you need to remember about the insert function is it inserts before, not after. Okay? So on Tuesday, we will pick up with deletion from a list. We will then compare that with inserting and deleting in the middle of a vector to show you why that is an operation you should not do unless you want to make your program run like a turtle. And we will get to doubly ended queues and a nice example of the use of lists. So have a good weekend, and I will see you on Tuesday.
I did send you a message on Canvas.